Hi, Prashant.
Hello, very good evening to you all.
Good evening, Prashant. Good evening. I have a small introduction for the entire community. Prashant, give me a minute.
Yeah,
Good evening, everyone, and welcome to today's Tech Talk, proudly organized by the Radio Society of Sri Lanka, or RSSL. I'm Titira, 4 Sierra 6, Tango Kilo Alpha, and I'm delighted to be your host and the moderator for this exciting session. The Radio Society of Sri Lanka, or RSSL, is the national body representing licensed amateur radio operators in Sri Lanka. It serves as a hub for innovation, learning, and collaboration in radio communication. Beyond supporting its members, RSSL also has have made significant contributions to the community. A standout example was during 2004 tsunami disaster, where the society provided vital disaster relief emergency services. Today, talk focuses on a revolutionary area of technology, LEO satellites or low Earth orbit satellite, internet and direct satellite to phone connection. These advancements are reshaping the way we connect, improving global broadband access, enhancing mobile networks, and providing critical solutions in disaster scenarios. Our speaker today is none other than Mr. Kusal Leopard, call sign 4 Sierra 7 Kilo Echo, also Victor Kilo 2 Kilo Sierra Lima. Currently based in New South Wales, Australia, Kusal is also a senior wireless architect at a telecommunication authority in New South Wales. He's also a chartered engineer and an active volunteer of Radio Society of Sri Lanka. He also served as the honorary secretary of Radio Society of Sri Lanka from 2002 to 2005. So we are incredibly grateful to Kusal for taking the time to join us after his working hours. So it's basically late at night on Sunday, especially on a Sunday, to share his expertise on this cutting edge topic. So before we begin, I'd like to highlight learn.rssl.lk, RSSL's newly launched learning management portal. This exclusive platform is designed to help our members prepare for the upcoming radio examination in the new year. If you are not already a member, this is a perfect time to apply and take advantage of this fantastic resource. Here's the plan for today. Kushal will begin with his presentation and then we'll move to a Q&A session. For those watching on YouTube, feel free to drop your questions in the live chat, of course, and I'll make sure they are addressed during the Q&As. Also, the ones who are in the Google Meet meeting, you can ask directly in the Q&A session. Kushal, over to you. Thank you.
Thank you, Titira, for the introduction, and very good evening to you all. So the topic for presentation today is the future of connectivity, low Earth orbit satellite communication. There has been a lot of new technological development recently on low Earth orbit satellite communication, especially after the launch of Starlink. And then recently this year, regulatory approval was given for Starlink operations in Sri Lanka, and also direct satellite to phone communication, which is operational in some parts of the world, and next year we can expect official launches in many other countries. So in today's presentation, we will look at how satellites provide connectivity with the overview of what low Earth orbit, medium Earth orbit, and geostationary satellites are. We will look at LEOSat applications, the advantages, disadvantages, and the technological challenges that we see in these operations. We will also look at who the major LEOSat operators are. And also we will look at developments in direct satellite to phone services and what the future outlook is for these services. So how does a satellite provide connectivity? A satellite is actually an object orbiting the Earth, and it acts as a relay station for communication signals. It can transmit and receive data between an Earth station and a user terminal. It's similar to a radio base station. As you know, in cellular mobile communications, we have radio base stations. Usually, they are located on a hilltop, on a tall building with a tower and an antenna. So the location at a high altitude is to provide coverage to a wider area. We can consider the satellite as a radio base station in the sky because they are up in a high altitude. It can cover a wide area, providing radio coverage to wide area, sometimes many countries at once. So what happens is a ground station will send a signal to the satellite. The satellite receives it, it amplifies it, and then retransmits it back to another ground station or a user terminal. Can be directly to a user device or to an antenna on a rooftop and to a user terminal. The satellite's orbit determines its coverage area. If it's very high in altitude, it can provide a vast area. Low Earth orbit satellites will provide lower coverage. And the ground stations are located on Earth, and they communicate with the satellites, and they also connect to the public telecommunication network. The ground station is responsible for transmitting and receiving signals, as well as controlling the satellite's operations. So let's look at the three different types of satellites we have today. The low Earth orbit satellites, they are satellites which are at an altitude of between 160 to 2000 kilometers above Earth. Then we get the medium Earth orbit satellites between 2000 and 36,000. Anything between the LEO and geostationary are considered as medium Earth orbit satellites. And then we have the geosatellites, the geostationary equatorial orbit satellites. This is a type of satellite that are carefully positioned at a particular height, 35,786 kilometers above Earth in a geosynchronous orbit to remain stationary over one point in the sky relative to the Earth. So when you look at it from the Earth, it is stationary, but actually it's in an orbit and it rotates every 24 hours around the Earth. But relative to the Earth, if it's rotating at the same direction, for us it appears as stationary. So let's look at how satellites are placed in orbit. Initially, a rocket carries the satellite into space, overcoming Earth's gravity. The rocket's upper stage provides a final push to place the satellite in its designated orbit. And once it is at the correct speed, is about 8 kilometers per second for LEO satellites, the satellite remains in orbit due to the balance between the forward momentum and the gravitational pull. So after insertion, no further propulsion is required, and the satellite continue to travel in orbit without needing any other power, except in the case of sometimes for orbital corrections, it will need a boost. So the satellites will have thrusters and boosters to use if needed. So that's how satellites are placed in orbit. So let's look at an important equation for orbiting satellites. In 1610, Johannes Kepler proposed three laws of orbital motion. And Kepler's third law states that square of orbital period is proportional to the cube of the orbital distance. And it's given from this equation, which means that this is the distance from the center of Earth to the satellite, is depicted by A, and P is the orbital period. All others are constant. M is the mass of the Earth, G is the gravitational constant. And what this basically means is if the satellite is closer to the Earth, it orbits at a faster time, less time to orbit the Earth, and when it's further away, it takes a longer time to orbit the Earth. And why this equation is important, we'll look at it in the next slide. Again, the same equation. So I've replaced the constants with the letter k for simplicity. A is the distance from the center of the Earth, p is the orbital period, and m is the mass of the Earth. And when you apply this for a LEO satellite, 550 kilometers above Earth, the orbital period is about 95 kilometers. Medium Earth orbit satellites, 20,000 kilometers above Earth, 12-hour satellite period. Now geostationary satellite, this is a very important figure, 35,786. And how was this calculated? If you apply the orbital period as 24 hours here for P, you have to convert it into seconds and put it there, we get this distance. So this is the height that we need to place geostationary orbits, geostationary satellites in orbit, so that relative to the Earth, it appears stationary. And also, this equation can be applied to any other object, even for the moon. For the moon, if you apply the distance from Earth to the moon, 360 kilometers, you get the 27-day orbital period. So that's Kepler's third equation. And this was initially proposed in 1945. Sir Arthur C. Clarke published the article Extraterrestrial Relays in the magazine Wireless World. And this is the article. He proposed the use of satellites in geostationary orbit for global communication coverage. He defined the orbit at this height, 35,786 kilometers, where the satellites appear stationary relative to the Earth's surface, and suggested that the satellites could act as a radio and TV relay station and enabling global connectivity and communication. So at that time, the word satellite was not used. He proposed saying that if you place 3 rocket stations at this particular height, it can virtually cover the whole globe. And he discussed the use of microwave radio frequencies and the feasibility of continuous coverage. His idea laid to the foundation for modern satellite communication, including TV broadcasting, GPS, and internet services. And the Clarke's prediction earned him the title the father of satellite communications, and this geostationary orbit is sometimes referred to as the Clarke orbit. So that was in 1945, and the first geostationary satellite, SYNCOM-2, was launched in 1963, proving that Clarke's vision is feasible. And today, there are over 500 satellites in geostationary satellites in operation today. So here is a comparison of geostationary, there's a spelling mistake, geostationary, medium Earth orbit, and low Earth orbit satellites. So the geostationary satellites, 36,000 kilometers, 8,000 if you take an example for medium Earth orbit, and LEO satellites, 1,000 kilometers. An important feature is the latency. Now, latency is the delay for end-to-end communication, the delay for a signal to travel from one end to the other. And for geostationary satellites, it's about 500 to 700 milliseconds. It's quite high because the signals have to travel 36,000 above Earth and come back. Medium Earth satellites, Earth orbit satellites, between 60 and 150 milliseconds, and LEO satellites, because they are less than 1,000 kilometers, it's between 20 and 60 milliseconds. So usually if the latency is over 125, 150, it becomes noticeable to a listener in a voice conversation. And for some of the applications, even if it's above 50 milliseconds, it's noticeable, especially real time, like gaming applications. So an important feature is your satellites the latency is very low. So how many satellites are needed for global service? For geostationary, 3 satellites can provide global coverage, almost the whole world. Medium Earth orbit, between 6 to 12 satellites, and LEO satellites, the figure varies. It can be 50, 60, or even 1,000, depending on the capacity and the areas served. How many data gateways are required? Geostationary satellites will require a few, more number for medium Earth orbit. And for LEO satellites, you require large number depending on the number of satellites and the capacity that you are serving. To look at the technology readiness level, both GEO and MEO satellites, they are proven deployable technology, has been there for a long time. LEO satellites still in development, especially for high-speed satellite internet. A lot of development has taken within the last few years. If you look at the satellite design life, GEO satellites designed for about 15 years life, medium orbit satellites between 10 and 12 years, and the LEO satellites have a shorter lifespan of between 5 to 7 years. So let us see some of the examples of GEO satellites. Intelsat is one of the earliest GEO satellites, a large commercial satellite operator providing a variety of services, including broadband, video distribution, and mobile communications. SCS is another major satellite operator offering similar services. Eutelsat, a European operator with a focus on broadcasting and broadband services. Hispasat, a Spanish satellite operator serving Latin America and Europe. Inmarsat operates primarily in geostationary orbit. They have a few in medium Earth orbit as well, providing reliable global mobile satellite communication services for aviation, maritime, and enterprise sector. These are some of the examples for geosatellite operators. There are a few others as well. Medium Earth orbit satellites, some examples, most of them are navigation satellites. We have the NavStar, which is the abbreviation for Navigation Satellite Timing and Ranging, commonly known as GPS, Global Positioning System, operated by the US government. Then we have the Russian GLONASS system, navigation system, Galileo, the European navigation system, Beidou, the Chinese navigation system. They are all on medium Earth orbit. And SCS-03B is a medium Earth orbit satellite service provider providing high-speed, low-latency broadband internet service to remote and underserved areas. And who are the LEO satellite operators? We have Iridium, just been there for over 20 years, providing mobile satellite communication services for voice and data. Global Star also has been there for over 20 years. Then we got Starlink, which was launched a couple of years ago, providing high-speed, low-latency internet access to remote areas and also urban areas as well. OneWeb, another LEO satellite operator, providing connectivity for business and governments. And Amazon Kuiper, it's an upcoming satellite constellation aiming to provide global broadband internet access. So what are the applications of LEO satellite? They can provide global internet connectivity. They can also provide direct satellite to phone services. We'll look at it in detail later on. That is the telephones, the smartphones we use, they can provide communications directly with the satellite. IoT, Internet of Things applications like various types of sensors, which can connect to the satellite and provide information. Maritime and aviation connectivity, Disaster recovery and emergency communication, a very important factor. When other infrastructure services are not available, you can directly connect to the satellites and provide communication for disaster relief operations and also for military applications. So this is a basic satellite network diagram, how it operates. We have the satellite Earth station or the gateway station, which is connected to the public telecommunication network. And from this Earth station, there are the feeder links, what we call the backhaul links that provide connectivity. And then we also have inter-satellite links. The satellites communicate with each other if say one particular satellite is not in line of sight of an Earth station, it can provide an inter-satellite link to the other satellite, and then it can connect to a gateway station. And the satellites can directly connect to a user terminal or to an antenna on a rooftop dish type of antenna and connect a user terminal. So this is how basic satellite connectivity diagram, how satellites provide data connectivity. Low Earth orbit satellites move at approximately 7 kilometers per second, and the orbital period is between 90 to 100 minutes. And it has a 15 to 20 minute pass time from horizon to horizon. So from a particular point in Earth, you will be able to get line of sight for about 15 minutes for each satellite. And before one satellite disappears over the horizon, there should be another satellite coming to provide continuous connectivity. So one satellite can have multiple ground stations connected, and also one ground station has multiple satellites connected. These ground stations, not every country will have a ground station. Some of the countries will have multiple ground stations, which is connected to the public internet, public telecommunication services. And what are the advantages of LEO satellites over other two types of satellites, the GEO and medium Earth orbit satellites? These are less expensive to launch and replace. They have lower transmit power requirement for both satellite and user terminals. They can support higher data transfer rates because of the shorter signal path. Because they are closer to the Earth, there is less signal attenuation, and that's why you require lower transmit power, low latency, less time for the signals to go from one end to the other, which all lead to faster data transmission. And they also use the higher frequency bands, which again helps for more data capacity. They use advanced electronic beam forming techniques for directing the beam antenna beam to a particular position on a particular area, which can be electronically steered, and also use adaptive modulations depending on the attenuation in the signal path. And they provide multiple satellites can provide overlapping coverage, increasing capacity. So for more capacity, several satellites can cover a single area to provide more data capacity for large number of users. And are there any disadvantages? Yeah, there are some disadvantages as well. The LEO satellites, because there are a large number of satellites, many satellites are needed for continuous coverage, which requires high deployment and maintenance cost for the constellation of satellites. Therefore, more complex network management, managing a large number of satellites is complex and challenging. And large number of frequencies are used, so may interfere with other satellite systems, potential interference. It also can result in orbital debris and space congestion because of the large number of satellites. And usually, if it has a lifespan of 5 to 7 years, at the end of the lifespan, they have to enter the atmosphere and burn out, or they have to be parked in a graveyard orbit. So, potential for space congestion and orbital debris. Also, orbital decay, because LEO satellites are closer to the Earth, they can experience rapid orbital decay due to atmospheric drag and require frequent reboosting and regular orbital adjustments and constellation management. And there are also regulatory hurdles, like for each country, obtaining permits and licenses for LEO satellites can be challenging because you need, although it's guided by ITU regulations, each country has its own regulatory regime, and you need to get the approval from each country for these frequencies used, and can be a tedious, cumbersome, and lengthy procedure. And the technical challenges, signal delays and fluctuations, timing variations due to altitude. So these are the challenges which needs to be addressed. Large Doppler shifts due to satellites moving at thousands of kilometers per hour. So as you know, transmitting source, if it's traveling at a high speed, at the receiving station, we can experience a slight shift in frequency. So that's called the Doppler shift, and that needs to be addressed. And also there can be signal degradation due to weather, atmospheric conditions, free space path loss, and shadowing. Because the signals are weaker, there can be interference and security attacks and jamming. There can be line of sight challenges. Sometimes the terminal on Earth may not have line of sight, or it will not have good view of the sky, especially if it's inside a building, unless they have an outdoor antenna. And also timing and synchronizing issues. So these are the technical issues that needs to be addressed in LEO satellite constellations. So let's look at a few low Earth orbit satellite systems that are in place now. Iridium satellites is the first one. Iridium has 66 active satellites in 6 orbital planes in low Earth orbit at an altitude of 780 kilometers. It has complete global coverage, including the polar regions. Started in 1998 and achieved global coverage in 2002. And it requires a special Iridium handphone like the one shown here. And it's primarily aimed at commercial and government users with a focus on maritime, aviation, and remote communications. And it's not usually used by the retail consumers, and it's not cheap either, expensive. The usage can be expensive. It uses the L-band frequency between 1 and 2 gigahertz. And by 2024, 1.8 million subscribers have been there. The applications are voice, data, and messaging service, IoT devices, machine-to-machine communications, using specialized devices like satellite phones like this. They also have a new project called Project Stardust, which plans for a satellite to cell phone service to be known as Project Stardust, that will support 5G messaging and emergency communication using a version of narrowband Internet of Things standards designed specifically for non-terrestrial networks. And they are expected to begin testing in 2025 and to launch in 2026. Globalstar is another LEO satellite operator. They started service in year 2000. 48 active satellites in low Earth orbit at an altitude of 1,400 kilometers. Globalstar also provides the infrastructure for emergency SOS via satellite functionality for Apple iPhones. We'll look at it in detail later on. And Globalstar phones looks similar to this. This is one of the models. You need special Globalstar satellite phones to use the service. They operate in L and S bands. Has global coverage, almost the whole world, excluding the polar regions and some countries, and have approximately 750,000 subscribers. They recently upgraded their ground stations to cater for increased capacity in iPhone messaging, which Apple is planning to launch next year. Starlink, that's the game-changing technology, which was launched about 2 years ago. Already they have over 7,000 satellites launched, with plans to go up to 34,000 and even more. LEO satellites at an altitude of about 550 kilometers. Their generation 2 satellites will be at a low Earth orbit at around 350 kilometers. So the configuration is large number of small mass-produced satellites. They also use laser crosslinks for inter-satellite communications, which gives increased capacity and reducing latency. And they use phased array antennas, providing high-speed data transmission to ground terminals. So phased array antennas can provide electronic beamforming, and you can dynamically direct the beam to the required areas. And even the user terminal dish antennas have the phased array antennas, which can track a satellite using electronic beamforming. And the user terminals they are compact and easy to install dishes that connect to the Starlink network. Already 4 million subscribers, and they operate in the Ku and Ka bands. And for future use, they will use the V band, E band, and the millimeter bands in the 70 and 80 gigahertz frequencies as well. So let's have a look at the satellite Starlink user terminals. There's one pictured here. It's a flat panel phased array antenna. Initially, when it's installed, the earlier models had a motor-driven setup. So when you initially install on a rooftop, the motor will rotate the antenna for the best view of the sky. And then after that, it rarely moves. After that, the electronic beamforming takes over and it tracks the satellite electronically. So only for initial setup, the motor-driven rotating of the antenna is done. But some of the later satellite antennas didn't have this setup. You need to point it in the sky, and there was an app in the phone to slightly adjust it to get the best view. Then it connects to a router, which provides a Wi-Fi bubble, and also it has Ethernet ports, can provide a Ethernet connection through a Cat5 or 6 cable, Ethernet cable. And they are compact and portable, allowing easy installation at homes, businesses, or remote locations. It doesn't require specialized technical skills. They have different packages for mobile users who can install the antennas on top of caravans or vehicles, and for portable use as well. The one pictured here is a mini Starlink antenna. It is slightly larger than an A4 size paper sheet. It can be carried with a backpack. And it has the plug and play setup. Once powered, it automatically connects to the satellite network. Starlink users typically experience download speeds between 25 and 220 megabits per second, and the majority of users experiencing speeds over 100 Mbps. Upload speeds are typically between 5 and 20 Mbps, and the most important thing is the data is not capped, unlimited data capacity. Eutelsat OneWeb, there's another LEO satellite operator. They have 630 satellites in 12 orbital planes, 1,200 kilometers above Earth. OneWeb is available across the globe and provide internet speeds up to 190 Mbps. And it uses the Ku band and the Ka bands. Ka bands is for intersatellite communications, and Ku band for connection between the satellite and the user terminals. OneWeb's constellation is particularly well suited and targeted at enterprise applications, offering high-speed, low-latency connectivity with guaranteed bandwidth. And it's usually used by commercial agencies, businesses, and government agencies. It's not usually targeted for the retail consumer users. It's an enterprise-grade service. Then another upcoming service, Amazon Kuiper. They also aim to provide high-speed, low-latency internet to rural and remote regions, and also urban, unserved and underserved communities. Plans to deploy about 3,200 satellites in low Earth orbit. Launches planned in stages. Initial deployment, initial operational capability expected by 2026, using Ka band frequencies and phased array antennas for efficient data transmission. Plans to offer affordable internet to individuals and businesses with seamless integration with Amazon services like and devices like AWS and Alexa. And they can leverage on Amazon's expertise in technology, logistics, and cloud computing to deliver reliable service. And one important application of LEO satellite is to use it as backhaul. Now, we all know cellular radio base stations, they need a backhaul service to connect to the core network, the 4G or 5G or 3G core network. Every cellular network has to be connected, every radio base station. And the usual method of connection is by a fiber connection or microwave links. Now, in remote areas, fiber connectivity may not be available, and it may be difficult to get a microwave connection. It may be a hilly terrain, or maybe the distance is too far. Now, in such instances, LEO satellite links, because of its low latency, can be used for backhaul connectivity. It's an attractive alternative, and because of that, to provide cellular connectivity for remote areas, this is a very attractive option. It can also be used to backhaul cells on wheels, which we call COWS. Cell on wheels is a transportable radio base stations which are deployed usually in special events, like if there is a high crowd capacity for temporarily for a few days. These base stations usually carried as a trailer attached to a vehicle. These are transportable radio base stations. Still will need a backhaul link to the core network, and satellite internet can be used for the core network. And also in a disaster situation, if the cellular infrastructure is damaged, you can transport a cell on wheels and deploy it with with satellite backhaul. And also in some areas where fiber backhaul or is not like feasible, if it's too expensive, can use that. And also as a backup solution to improve reliability in areas where terrestrial backhaul is susceptible to natural disasters. To give an example, in Australia, about 300 Telstra radio base stations are now linked through OneWeb satellite backhaul in very remote areas. Most of them actually initially were linked using geo satellites, but now with OneWeb LEO satellites, they have improved the speed by over 15 times and reduced the latency by 10 times when they change from geo satellite to LEO satellite. So one of the optional uses of LEO satellites is to backhaul cellular mobile radio base stations. Now let's look at phone to satellite direct calling, another revolution in mobile connectivity. It can bridge gaps and enable seamless communication from virtually everywhere. Traditional cellular networks often fall short in remote areas or during natural disasters, leaving users stranded without a connection. And the option has been satellite phones for these scenarios, but they have been limited by their bulk, expensive, and specialized equipment requirement. You need to have a separate satellite phone. The usage was expensive, so that has been the option. But with these new developments, the ordinary smartphones we use would in future be able to connect directly to satellites. So the recent advancements in these satellite services, since they orbit closer to Earth, reduce latency and improved data transfer speeds. And the new technologies enable direct communications with unmodified smartphones, which remove the need for specialized equipment, and they can seamlessly integrate with the cellular network, providing seamless connection. That means if you are in an area without cellular connectivity, only it will connect to the satellite. If the cellular signal is present, it will use the normal cellular mobile network. And it can provide bridges in coverage gaps, rural areas, and during natural disasters. Very important aspect, enabling emergency communications from any location, expanding the mobile reach, and the ability to send emergency alerts. Now, imagine in a disaster, if the cellular mobile infrastructure is damaged, there may not be a method to send messages or communicate with the people in the area. One alternative would have been radio and television, but that can also be damaged, and not many people would be listening to radio or watching TV. But if you have direct satellite to phone communication, you can send messages to targeted areas direct to the phone. For instance, you can send an evacuation message in a flood situation to a specific area, things like that. These are the advantages of phone to satellite, satellite to phone connectivity in emergency situations, ability to send emergency alerts. Let's look at who the key players are in the satellite to phone area. Apple is on top at the moment, integrating satellite connectivity into its iPhone 14 and later models using the Global Star range of satellites. Then we have the AST Space Mobile. It's a pioneer in direct-to-device satellite communication with its Blue Walker 3 satellite. Then we have Link Global, which is developing a network of low Earth orbit satellites to provide global satellite-to-phone coverage. And Starlink also plans to roll out direct-to-cell tech service in 2024. We are already at the end. They have done a lot of testing. Probably they may officially announce it before the end of the year, followed by voice data and IoT connectivity in 2024. So Starlink at the moment provides internet connectivity to dish antenna. This is in addition to that another service, direct to phone services. And let's look at the Apple service. So Apple has this ability, the emergency SOS service via satellite. It's a feature available on iPhone 14 and beyond, which allows users to connect to emergency services when cellular Wi-Fi coverage is not available. That is, if, for example, if you go on a hike and you are in a medical emergency, if there is no cellular coverage, you can use this service in countries that this service is already available. It uses global star satellites to provide the infrastructure for these services. And they use the L band for uplink and the S band for downlink. It was launched in 2023. It's available in 16 countries: USA, Canada, UK, some European countries, Australia and New Zealand. And it will be expanded into other countries as well in future. And Apple has said it's 2 years of free service. They haven't said what's going to happen after 2 years, whether they are going to charge the service. It seamlessly integrates with the existing fall and crash detection capabilities of Apple devices. As you know, the Apple Watch has the crash detection feature. And if it detects a crash, and if you are in an area where there is no cellular coverage, but if the phone can get the satellite connection, it can send the message from connected Apple devices. It will send up the information, the medical ID if it's properly set up, your emergency contact information, the location, and the iPhone battery level. So these are only for emergency use at the moment. But in addition to that, in USA, the roadside assistance for vehicle breakdown is also available. That is, if your vehicle breaks down in an area with no mobile coverage, you can use this service. And the breakdown assistance services like the AAA, the American Automobile Association, and other agencies will come into your help. So at the moment, this is available only in US. And next year, they are planning to launch messaging via satellite with iOS 18. So in addition to emergency messaging, it will enable for iPhone users to send ordinary messages to other users using this feature, initially planned for USA and gradually expanding into other countries. So that's a very exciting development. And the question that comes into most Sri Lankans' minds is this service available or when will it be launched in Sri Lanka? So unfortunately, the Global Star satellite primary coverage footprint does not include Sri Lanka at the moment. So it will be a few years before Sri Lankan iPhone users will be able to use the service until they expand the service. At the moment, uh, there has not been any indication when it will be launched in Sri Lanka. So only 16 countries has this service, but gradually the plan is to provide this service globally. Then another service that is currently available, the Google ESOS service. It is provided by Skylo, is the satellite operator, and this is currently available in USA only, not including Hawaii and Alaska. This feature is available in the Pixel 9 range of phones only, and Google has said 2 years of free service. So far, other Android has not made an official announcement, and for the Android users, a lot of testing has been done by other users, but no official announcement. But 2025, most probably we will see the launch of services for Android users as well by other companies like AST and Link. So this is the other company that is planning to provide the service. They plan to provide direct connection to existing cell phones seamlessly using Link's LEO satellites. 8 satellites have already been launched. Plans to have 38 by year 2025, 74 by the next year, and eventually 5,000 satellites. Voice and SMS messaging initially, with plans to offer high-speed data later on. Complementing networks, like directly augmenting existing terrestrial networks, ensuring connectivity everywhere. They have entered into service agreements with more than 40 mobile network operators globally for this service already. In April, Link announced a contract with the US government to provide satellite direct-to-phone services to the Department of Defense and Department of Homeland Security and other US governmental organizations. AST Space Mobile is another service that plans to offer these services, which is also, they say, will be accessible by standard smartphones. It has partnered with over 45 mobile network operators already, which has a customer base of 2.8 billion cellular customers. The company's Blue Walker 3 prototype satellite is the largest commercial communication array in low Earth orbit, similar to one pictured here, large antenna. They successfully launched the first 5 Block 1 Bluebird operational satellites this year, and 17 more are being built. In USA, they plan to use the 850 megahertz, which is currently being used by AT&T and Verizon. And they have conducted tests and demonstrated that preemption, mission critical push to talk, and mission critical video services can be supported over satellite direct to phone connectivity by ST Space Mobile. The mission critical push to talk is like the emergency services they use, push to talk services similar to the ones we use on the amateur radio operators use. This can also be used through satellite according to AST, and they have already done the testing and demonstrated it. Then we come to Starlink. They are direct to cell services, another revolutionary service from SpaceX, which seamlessly integrates with existing cell phones. providing global coverage, including remote regions. Enhance, planning to provide enhanced voice and data services, rolling out SMS messaging in 2024. That's what they had announced earlier. They did a lot of testing in USA, followed by voice and data in 2025. It complements SpaceX existing Starlink satellite internet service, and not all LEO satellites support this service. So over 320 satellites with direct-to-cell payload have been launched out of the 7,320 support this service, and they plan to launch more direct-to-cell satellites in future. So that's from Starlink. Just to give one example of testing that has already taken place in USA, SpaceX did this testing with T-Mobile, a US mobile operator. They are planning to aim follow LEO satellites for cellular coverage on existing 5G smartphones across USA using 1900 megahertz spectrum that is being part of the T-Mobile carriers 4G and now the 5G network. So according to a recent press release, satellite connectivity will allow you to send text messages, including SMS, MMS, and access select messaging apps. The company also hopes to add voice and data connectivity in future. Starlink direct to mobile phone internet is exclusively with T-Mobile in USA for the first year, and then other carriers, Elon Musk's Proton's X. We are starting off working with one carrier in each country, but ultimately hope to serve all carriers. So their plan is initially with one cellular carrier and then give the services to other carriers as well. So let's look at the importance of 3GPP. 3GPP is the 3G partnership project, which standardizes the cellular mobile standards and the non-terrestrial networks. So 3GPP is working to standardize direct-to-phone satellite direct-to-phone communications via low Earth orbit satellites, enabling seamless connectivity for regular smartphones by integrating satellite networks into 5G infrastructure. Non-terrestrial networks, NTNs, are being developed to seamlessly integrate with 5G networks, supporting wide range of use cases from consumer mobile broadband to machine type communications. And in their release 17, they have standardized some aspects of non-terrestrial networks, focusing on aspects like the waveforms, protocols, and architecture to ensure that satellite networks can interoperate with existing terrestrial mobile networks. They were addressing latency, managing the Doppler effect due to satellite movement, and ensuring efficient use of spectrum. They are the key technical challenges that the 3GPP works groups are tackling. So all these LEO satellite operators have said they are committed to adhering to these standards in future. At the moment, some may not adhere to these 3GPP standards because now we are still in the early stages, but in future, they will. They have said that they are committed to adhering to these standards. So what's the future outlook for these services? Phone-to-satellite direct calling is transforming the mobile connectivity. It can bridge gaps in traditional cellular networks. It can enable access to emergency communications from anywhere. Your satellites provide near-instant wide area coverage, enabling direct-to-phone emergency warnings, even in remote or disaster-stricken areas with no ground infrastructure. The technology is maturing and expanding. It does not replace, but complements cellular, mobile, and fixed services. So that's an important point. because this is not a replacement for cellular mobile coverage. The best connection for internet is fiber to the home, and nothing can match that. And then cellular mobile, because radio waves are shared, cellular mobile is next. But if both are not available, then this can complement that service. But due to the distance from user terminal to the satellite, over 500 kilometers, the attenuation is high, and the cellular phones have very low transmit power, about 200 to 250 milliwatts. Therefore, it's really challenging, and you need to add a lot of overhead, like extra error correction bits, because there can be a lot of free space attenuation due to the distance. So these can complement the existing cellular networks, but will not be a replacement. Even broadband internet in areas where fiber is not available, this is a good option. So they will play a crucial role in supporting 5G and beyond, particularly in underserved and remote regions. 3GPP and NTN are enabling seamless connectivity between 5G and satellite networks. Regulatory hurdles and space debris management remain significant challenges as the number of LEO satellites increases. Further improvements in satellite design, such as the use of laser-based inter-satellite links and AI-driven traffic management, will further enhance network performance and coverage. So a lot of developments taking place, and next few years we can see the results of these developments. And that brings us to the end of the presentation. So if you have any questions or any discussions can take place now.
Hi, Kusal. This is Deep. Can you hear me?
Yep.
Yeah, nice talking to you again. So I read like for SpaceX, the current rocket can take around 8,000 kilograms, right? So they are Falcon 9. The other one is the bigger rocket is Starship. They are talking about 1,000 kilograms, right? Sorry, 1,000 ton. Yeah, 1,000 ton, 100 tons, and the Falcon 9 is 22. Sorry, 8,000 kilograms, so 8 tons, right? So what will make what that Starlink, if we can send that kind of a large satellite, I don't know. So what difference it will make in the communication? Like,
Usually, actually, I don't know the weight or the size of. Usually, LEO satellites are not very large satellites, but the concept is to provide large number of satellites, and rocket can take multiple satellites. It's not only one. They take a few satellites at a
yeah,
given instance and launch it. So to give coverage, you need to cater to the capacity. Now, just like cellular base stations, if you look in urban areas, you have more number of base stations close together to provide more capacity. So that's why in LEO satellite, you will need large number of satellites to cater to the capacity. And that's the concept behind this, because in geo satellites, if you have a few satellites, everybody has to share the services, and that frequency will not be able to, a particular radio frequency cannot supply that capacity. So that's why it's the satellites are mass produced and you deploy a large number of satellites. So that's the concept in low Earth orbit.
say they are going to create like a larger, like a heavyweight, like with when you say increase, they can send like high larger satellites. I mean, even for the geos the low orbit. That since I think the current stuff are very small satellite, but if they increase the power, what will that make? Like can we?
You mean the transmit power?
Yeah, something like that. I imagine something.
Yes. Yep. So definitely increase the transmit power will give good connectivity, but that will also have impact. You will need large batteries and larger solar arrays for that. And also, then the other thing is from the ground terminal side also, you need to increase the transmit power. Now that may have limitations because it depends on each country's regulatory authority. Like if a large number of satellite dishes, if the power is increased, that can cause interference. So there are issues in it because it's a two-way communication. So there can be limitations. So Starlink has different types of satellites. Now their generation 2 satellites will be different. To that, I haven't read much about it, but they're going to be at a lower Earth orbit now. The generation 1 satellites were about 550 kilometers up. Gen 2 satellites will be at a lower orbit at 350 kilometers. That's what they have said.
Okay, thank you.
Kusal, Maruna, my question is, Kusal, when they place a low orbit satellite, I feel that they need higher energy to maintain the satellite. Basically, because it's because of the gravitational force, it tends to come to the Earth, really. So maintaining how they can be, how they are going to find the energy for that.
Like if I go to a previous slide, actually they don't require, once it's placed in the correct orbit, they don't require any more power because of the, okay. Yeah, after the insertion, you have the gravitational power and also the vertical speed that is launched. Due to the balance of these, you don't need any more propulsion. It will continue to orbit the Earth. And then if there is a slight, if it's misalignment in the orbit or it goes out of the orbit due to atmospheric drag, then they have the thrusters and boosters to that will work on usually battery power or chemical power to correct the orbit. Other than that, when the object is orbiting the Earth, they don't require any power. So that's due to the formula I explained, because there is a balance between the gravitational pull and the vertical speed.
All right, thank you. My other question is, can you hear me, Kusal?
Yeah.
My other question is, these satellites, basically the large amount of satellites, whether now the big satellites, I know the space crafts goes there and basically do the maintenance and kind of things. So how what kind of a methodology they use to maintain those satellites, basically, when there is a technical defect, or are they bringing down to Earth and repair and, shoot it back to orbit, or are they, what kind of thing they do?
So usually low Earth orbit satellites, they have a shorter lifespan. At the end of the lifespan, they sort of make it to deorbit, and when it enters the atmosphere, they burn out. So that's the way. The larger geostationary satellites, there is an orbit called graveyard orbit. They sort of take it there and place it, and there are organizations that monitor the satellites and the space debris. So there has to be coordination between them, and even when you launch a rocket, it should not crash with the existing satellites. So there are organizations that that will provide the orbitals, dots, and these launches. All this has to be properly coordinated.
Thank you, Kusar. I think we
Okay.
got a lot of good information. Thank you very much for sharing your expertise with us.
Yeah.
Thanks a lot.
Tarang and Alex, yeah.
Yes.
Hi, good morning. Well, morning for me. The satellites in these constellations, how are they communicating with each other? Is it traditional RF communication? I've heard things that some of them are using or plan to be using laser communication. What is the common case here for communication inter-satellite?
Yeah, so the Starlink, they are using laser communications. That's in the optical frequencies in the terahertz range, and therefore they can achieve high speeds. But the other OneWeb, they are still using radio links in different frequencies. That's how intersatellite communication take place, and also the frequencies usually satellite used to communicate with the ground station is different to the frequency that the satellite used to communicate with the user devices.
Okay, so the laser technology is fairly new, and that's
fairly new. Yes, Starlink is already using.
They're the only ones using it right now.
Yeah, that's what I know. Others haven't indicated it. It's fairly new. Yeah.
Thank you so much.
Taranga?
Yeah, Kusal. Well, I'm just trying to understand the architecture of these low Earth orbit ISPs. So,
Yep.
say that I'm trying to access or I'm trying to get some information from a server on the other side of the world.
Yeah.
And does it still have to go through because the footprint is so small? Does it still have to go through so many hops to reach that data center or the server?
Well, it depends. It depends on where the data center is located and how the traffic is routed, because not every country will have a station. For instance, if you are using this terminal in Sri Lanka, there won't, at the moment, if there is no Earth station in Sri Lanka, probably it will go through another hop to another satellite and connect to an Earth station in another country. Then from that country, it connects to the gateway station, and then from that gateway station, it needs to go through probably a submarine cable to the particular data center where it is located. So, as you know, the submarine cables, there are different organizations that operate it, like the CMEV range cables. Then companies like Amazon or Facebook, they have their own submarine cables. It depends on where the data center is located and from where you are accessing the service.
Right. So somewhere down the path, it still merges with the conventional the traffic route.
It has to. Yeah, it has to. Like it can be in the same country as well. Like probably, let's say in Australia, the first hop from the satellite could be a gateway station within the country, and if the data center is located within Australia, then it can directly connect from the gateway to the public telecommunication network and through to a underground cable. It's all depending on the routing protocols and how they are configured.
So if we compare that, or rather if we translate that into the speeds and the data rates, so the difference that the gain that these low Earth orbit satellite ISPs will have is the low latency. Actually the last mile. Am I correct? From the terminal to the.
That's right. Yeah. So that's the important part actually, because the free space communication, the last mile, that distance, 500 kilometers up and down, that's the lower latency compared to the geo and medium orbit satellites, which the latency will be much higher. And I don't know, some people may remember those taking international phone calls probably 35, 40 years ago, there were longer delays, but they are not there anymore because there are submarine cables. But yes, it depends on that latency part is in the way from your terminal to the satellite and back to the ground station. That part is the latency. You have to add the latency from here to the desired destination as well through the public telecommunication network.
Super. Right. Thank you, Kusal. It's wonderful. Thank you.
If you have any more questions, I think it will be the best time to ask. Thanks.
Kusal, I'm Kamal. Can you hear me?
Yes, Kama.
All right, Kusal. Yeah, I have a question like this now. You are talking about frequency allocations across various countries for these satellite services, right? Now, if you take I'm thinking about now a MEO satellite in the range of 2,000 kilometers above will have a large footprint for, let's say, it will cover India, Sri Lanka, China, South Korea, and the vast area, not like the LEO satellites, right? So when a particular country in that footprint objects to use such frequency, how is the satellite going to manage that using only beamforming? Can that be done? Is it practical?
For medium Earth satellites, it's not practical. The thing is, like, let's say the country's regulatory authority does not allow it, they can say you cannot use the services in our country, but still the satellite would be transmitted. But usually the frequencies are guided by ITU regulations. Still, the local regulations also have to allow it. Now, this is especially in the case of direct-to-phone satellites. In that case, they will be using the existing cellular bands. So that's the difficult part to agree. So the cellular mobile operators need to cooperate. They should come to an agreement with the satellite network operator and agree to share their frequencies as well, direct to phone. And the thing is, in the LEO satellites, it's easier to have the spot beams. They can steer the beams, and that's why even in Starlink, they can switch off the service to particular countries if they don't want. They do it actually currently. That's the advantage of LEO satellites, because the spot beams, the area is lower and they can cover targeted areas. But again, the difficulty is some of these frequencies might be used by other services, and
that's right. It's very hard to remove those services. So in that case, it's very difficult, right?
Yeah, that's right. That's a big regulatory hurdle. But I mean, gradually, everybody will come on board, but it will take time.
Right. Kusal, another question now. We were talking about when the competition goes high in the satellite communications, all these gigahertz and gigahertz, it going up and up, 60 gigahertz, 80 gigahertz, and so on, right? So everything is going to transmit from the heavens above to the down to us. And what is going to happen to us, actually? The remaining few hairs of ours.
If you look at the EME radiation, whether like it's harmful or not, now that's a very controversial debate. So the thing is, if you are guided by organizations like World Health Organization or the FCC or different organizations, what they say is like there is no conclusive evidence that it's harmful at the moment. There are isolated studies that says that okay, so these are harmful, but most of the studies have shown it's only the thermal effect, because this is non-ionizing radiation. So there is a lot of debate, a lot of controversial conspiracy theories. And the other thing is it's low power, very low power. Like if you take a microwave oven, it's 800 watts, 1000 watts, but the universal cellular phone, 250 milliwatts. And even in the microwave region, even in the satellite communication, it will be very low power. So the information available at the moment is like a lot of peer-reviewed research and all, that it's not harmful, although there are a few isolated studies to say, but the common understanding among the scientific community is no harm at the moment.
Okay. Right, Kusal. Thanks.
Istaranga.
Yeah, just adding on to what Kamal brought up. So, how susceptible are these frequencies to noise, the QRM and natural QRM also, when the frequency goes up and up, Kusal? And what sort of an impact will have it on the latencies and the data rates? Yeah, that's a question. Thank you.
Yeah, it has an impact, and also because of the distance involved, that's why a lot of overhead error correction bits need to be included in these transmissions. And especially, for example, the text messages as it stands today, when they are sent from a user terminal like a phone, like an Apple iPhone, usually in the cellular mobile network, you can instantly send a text message, but sometimes it may take 5 seconds or even 30 seconds to send a text message, because there are lots of overhead bits added, and it will keep on trying, and a lot of acknowledgements going up and down. So that's a challenge actually. And there are that's from the user, if you connect directly from the phone terminal to a satellite. But if you use a antenna for internet, like phased array antenna, the advantage is because of the electronic beam forming, when you target it to a particular direction, if there is noise from other surrounding areas, that can be kind of isolated and minimized, because when you send the signal, changing the phase angle, and you target a beam in that particular direction, you get the strong signal. So whatever coming from the other directions is minimized. So that advantage is there in electronic beamforming. Did I answer your question?
Sorry, I was on mute. Yes, Kusal. Yes. Thank you.
Kusal,
Over to
there's
you.
a question by Iftar. He's asking whether local regulatory bodies regulate internet services through.
You mean the amount? Okay. You mean the content of the internet? Yes. So as far as I know, the TRC has the power to block websites and things like that. So in this instance, the one thing is that satellite internet has the ability to bypass that. Yeah. Because then local regulatory authority cannot sort of manage the content in such an instance, but they can, I don't know, the legal point of view, they can give a ruling to block a certain website, like they do now. The thing is, like for cellular mobile operators and landline operators, they can give a ruling to block certain websites. They have done it in the past for security reasons and all. For satellite operators, whether that will work, I don't know. Technically, they are not capable, but the country's regulator can say, okay, and whether the satellite network operator would be willing to do that, I'm not quite sure about it, because especially if you look at Starlink and all, Elon Musk is very pro free speech oriented guy.
Thank you so much, Kusal, for the answer. Are there any more questions from the community?
One more question, Mr. Kusal. So, with the availability and the competition, the CUPA and all, the satellite internet will be much more cheaper. can you predict what kind of businesses will be generated and what will be the future like within next 5 years with this cheaper satellite internet? So can we start some new businesses to flourish with this like mobile revolution?
Yes, certainly, because we already have seen, I believe that previously we didn't have many packages with unlimited internet, and I saw recently that SLT has modified their packages, and now I'm not too sure whether it's cheaper than it was earlier when there is competition, and especially when Starlink is giving unlimited internet. Like if you want to start a business in a very remote location, now there is, it may not have the infrastructure, even electricity, but you can use solar power and then connectivity is there. So everything is will be available now. The limitation was mainly communications because it was not feasible to lay a fiber link or have a cellular base station, but this removes all the barriers. So any place in Earth, it has the potential for uh, high-speed data connectivity, and that's a kind of a game-changing technology for any service, maybe a business process outsourcing or tourist operation or anything. So that's because previously these services were not available for retail customers. Only the big organizations like the governments, commercial organizations had it. Now the cost has come down, and it's within the range of the retail customer.
Do you see any businesses coming up in Australia?
In Australia, I believe the thing is there are more than 10,000. So earlier in very remote areas, Australia is a large country and not even 30% is covered by cellular, mobile and others. They had this NBN, National Broadband Network. They had 2 geostationary satellites, SkyMaster 1 and 2. Now after Starlink came, most of the customers of this previous NBN satellite, they have transferred to Starlink because it's cheaper, provides higher speed, and most of the rural farms and all, they have improved their connectivity, especially they use the new technologies for farming and all, IoT, the sensors for crop harvesting and environmental sensors. All this has been possible, and there has been a lot of interest in that one.
Thank you, sir.
Are there any more questions for Kusa? Thanks. Dirisha, please go ahead.
Yeah, hi. I hope you all can hear me. My concern is what are the privacy concerns associated with these new satellite communication methods, such as the mass surveillance of governments and data breaches, hacking attempts, and all that. Because you mentioned earlier, not all countries have the ground stations for those satellite networks. So the ones which have ground stations are governed by those countries' laws. And what does that mean for the end user regarding the data privacy and privacy as a whole?
So some countries have regulations that like certain data need to be stored in their own countries. Now, I don't know whether Sri Lanka has come up to that stage. Yes, so it will go through gateways in other countries. It will be difficult to block, but the regulatory authorities, they need to adapt to those things, and you need to look at the cyber security aspects as well. And also the thing is, the satellite network operator, you are at the mercy of it. Like if the satellite network operator decides to switch off the services, it will be switched off. Like probably in a war situation, if the owner of the satellite network decides, okay, we need to switch off the services to this country, they will do it. So there's nothing can be done about it. And So that aspect is still there.
Yes, thank you, Mr. Usal. Thank you for answering the question. Thank you.
Yeah.
Any more questions from the community? Are there any final questions for the host, Kusal? If there is none, we could wrap up.
Yes, Tidra, if there are no more questions, thank you for listening and hope that you had gathered some knowledge and information on these services, and we can see some exciting new technological developments in the next few years.
Appreciate Kusal. Thank you so much for sharing your knowledge and making this complex topic accessible to everyone in layman terms, of course. So we deeply appreciate your commitment, especially joining outside from all the way from New South Wales. It's I think 2 in the morning. So a big thank once again, Kusal, and also a big thank to everyone who joined us today, especially from the overseas, the operators, and also the well-wishers and the other committee members, of course, and the other system members, of course. Your participation and thoughtful questions have truly enriched discussions. There's no doubt. And I would like to extend our gratitude to the president of RSSL, Taranga, 406 Tango Mike Papa, and Mr. Singer, 406 Lima Echo Oscar, for his technical expertise, as well as to the RSSL officials and everyone who worked behind the scenes to make this event possible. So RSSL's effort, including the launch of learn.rssl.lk, continue to pave the way of learning and collaboration. So we have a small issue with the website. We are fixing it, so it will be fixed in no time, of course. So this is just one of the many exciting sessions we have planned. Stay tuned for updates on upcoming programs, of course, and don't forget to explore our new members portal, the learning portal, of course, for more opportunities to grow and prepare for the upcoming radio examination. So thank you once again for joining us today. We look forward to seeing you in future events. Until next time, stay curious and stay connected. Take care. Taranga, Victor?
Yeah,
Thanks.
okay. Can you hear me, Tidra?
Yes, Victor, loud
Yes,
and clear.
Victor.
Loud.
Okay. Okay. I think we have taken a lot of time of Kusal, especially after midnight out there in Australia. But to make it possible for us at a more convenient time to listen to him and watch this wonderful presentation, Kusal has gone to great lengths of personal inconvenience. Kusal, we'd like to thank you very much. And also your great affection for the Radio Society and on our behalf to make this presentation. It was wonderful listening and the possibilities of the future and the problems and the benefits that it will give us. So thank you once again. I don't like to keep it any more longer. So thank you and all the best to Tizra and Taranga, Singer, also for the support and making it possible. Once again, thank you, everyone. And we'll meet on another occasion with another presentation. Thank you, Kusal, especially.
Thanks, Victor.
Thank you, Kusal. Yes, and the link for the video will be, it's actually already going live on YouTube. So if you visit the Radio Society's website, YouTube page, Radio Society of Sri Lanka, you can find the recorded video there, and we will make it available on the website also. So thank you very much, Kusal. It's been a pleasure to host this presentation, and you did a fantastic job. Thank you so much for it, and I think you have an early morning tomorrow, so good luck with the rest of the week, Kusal. Thanks again.
Yeah, thanks, Tarang, for organizing the event.